Why are so many things bell-shaped? Okay, I'll give you the quick answer first. Nobody knows. Nobody really knows why bell curves show up all the time. It's kind of like the golden ratio, the 1.618 or whatever it is. Why that particular ratio of rectangles is the most appealing to the human eye? Nobody knows. It just seems to be. And unlike the golden ratio, which is somewhat arbitrary and a little bit subjective, at least I think, numerically analyze why it makes sense that so many things are bell-shaped. And what I'd like to do to draw a connection to my thoughts on this over the past 25 years, I want to look back at something we looked at in the binomial distribution, which was Pascal's triangle. Now, Pascal's was this wonderful triangle of numbers that gave us the binomial coefficients that were harder and harder to get depending on how far down the triangle we had to get or how many chickens we had to purchase. I think Pascal's triangle could do a really, really good job of explaining where the bell curve kind of comes from the idea of random occurrences. Let's take a look at what I mean. We're going to build a plinko board or a wall board or the OMSI thing with the pegs on my chalkboard here. We're going to model it. We're not going to build it. I wish we could. That'd be fun. And the top of Pascal's triangle, if you remember, was just a 1. And don't worry about the fact that that top is a 1. That's just more or less a placeholder. But that's where we're going to drop our chip or our ball or that little tiny white sphere from OMSI. Now, if this was your entire plinko board, it's really, really boring. You drop the chip and it goes boop, and the game's over. And then whatever prize is in that bin, you win. That's kind of lame. So, generally speaking, the plinko boards those are longer. So that one right there would be the next row. This way, if you drop the chip or the ball up here, it's either going to fall to the left or to the right. Let's make an assumption for simplicity right now that it's equally likely to fall either left or right. We can adjust that later, but for right now, let's just say that if you put the chip here or the ball here, it's just as likely to fall to the left as it is to fall to the right. Well, these numbers here tell you how many different ways it can fall. Clearly, there are 2 total ways it could fall. It could fall left or it could fall right. And there's one of each. It either goes that way or that way. Again, kind of boring. Let's add the next row. Let's make the plinko board longer. So now, you can see 1, 2, 1. These are the coefficients for buying 2 chickens. What are these numbers actually telling us? Well, let's start at the ends. What is this one telling you? It says, if you drop a chip up here, there's only one possible way for that chip to make it to this area right here. There's really 3 areas here. These are kind of like the bins at the bottom of the plinko board or at the bottom of the wall board. Or in OMSI, right? All those little bins, I told you we were going to talk about them later, and here we're talking about them. This one says there's only one way to get into that bin. You have to keep making left turns. And as long as you keep making left turns, you're going to end up here. But there's only one way for it to happen. Think of the chip having a choice, a random choice. It's here. It has to choose to go left, and then it has to choose to go left again. That's the only way. Similarly, this one is because the chip chose to go right, and then chose to go right again. This 2 in the middle tells us there's 2 ways for the chip to end up here. It can either go left then right, or right then left. There's no other way for it to get here, assuming that it's not bouncing back up, assuming that it only can move down and left or right at each stop. Okay so far? All right. Let's go to the next row. This is where it's getting fun. And what you're also seeing now is, and we're going to take a look at this visually in Excel in a second, you're beginning to see the middle becoming larger and the tails tailing off. These tails up here were kind of boring, but now you can see there's 4 bins, and the tails are going to stay 1. The only way to end up at the extreme tails is to make sure that the chip either makes all left turns or all right turns. One way for that to happen. Why are these 3s here? Well, this 3, to end up in this bin, you can either come from this side or from this side. As I was just editing, I realized I wanted to clarify something. I made the assumption right here, in order to get to this 3, you have to come from either this 2 or this 1. And that's the mathematical assumption I'm making for the choice that the ball makes as it comes down. Now, looking at the OMSI video and the Plinko video again, that appears to be what's happening. I mean, it's possible that a ball could fall straight down, but you could argue if it's falling straight down, it's making a choice. It's alternating quickly, left, right, left, right, left, right, left, right. The only one where it might not be as neat and clean is in that wall video, because they're using some kind of it looks like an air-filled ball that could actually bounce. For example, using this Pascal's, it could be down here and then bounce clear across like this. I just watched that video again and a couple more. It happens a little bit, but not too much. I think the majority of the time, at least in the quick anecdotal survey I just did, majority of the time, ball hits a peg and then makes a choice either left or right. Well, there's only 2 ways to get from this side, and there's only 1 way to get to this side, so adding them together is 3, which some of you probably discovered if you did that extra credit about Pascal's in the last topic in the homeworks. Same as this 3. There were 2 ways to get here, 1 way to get here. You could also kind of do it old school and figure it out. Starting here, you could go bop, 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 that's 1 way. You could also go bop, 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 that's another way. Or you could go bop, 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 that's a 3rd way. So you could figure it out that way as well. Let's do 1 more on the board. Then I'm going to be out of space. And then we'll keep going on Excel. We'll actually analyze what Plinko looks like, what the wall looks like, and what OMSI looks like, and see if we can figure out where those shapes come from. All right, so the next line here is going to be 1, 4, 6, 4, 1. Now, you can get these numbers fairly straightforwardly by looking at the numbers diagonally above them and adding them together. But again, the reason that works is because it's also telling you, if this is 5 bins, it's also telling you how many paths there are possible to get to that bin. The 1 and the 1, I think we understand why those 1s are there now. Why the 4? Well, again, 2 different ways. 3 ways to get here, 1 way to get here. That's 4 ways total. Another way of looking at it, you can either be making your way all in the left and then cut back. That's one of them. You can make your way down, cut, cut, that's another one. Make your way, cut, 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 that's another one. Or cut, 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 cut. That's another one. There's your 4 ways. Let's see if I can figure out the 6 ways, and then we'll go to the board. I didn't put myself on the spot. I haven't tried this yet. Okay, 6 ways. We can go bop, 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 bop. Or bop, 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 bop. That's another way. So I'm going to do, if I could find 3, I could double it to get the other one. So I can go this way, this way. This way, this way, this way, this way. Or this way, this way, this way. That's 3 ways, and then just reverse it to the other side, and that's the 6. That's going to make your head explode, or at least it's going to make my head explode. So I vote we look at it using technology to see how Plinko and the wall and also the OMSI board are modeled, and see if we can see that curve showing up. Okay, friends, so I actually went back and looked more carefully at all 3 of these things, Plinko, OMSI, and the wall. And it turns out that Plinko and OMSI, I mean, I didn't get great resolution in the pictures I was looking at, but both of them appear to be about 13 rows high. So that Pascal's triangle we just started on the chalkboard, we'd have to continue it back down about 7 more rows. If you did that, this is what the coefficients would look like. Now, I did them in percent form. I didn't do them in raw number form. So in other words, I didn't tell you this is how many ways you can get to, say, this spot right here. I said 21% of the time you're going to get to this spot right here, which means 42% of the time you're going to get right to here. So this tells you something, right? Assuming you know how wide these things are, 42% of the time, or roughly 2 out of 5 drops from the top, is going to end you up between those 2 bars right there. If you pop out to these next few here, that's going to be roughly 75% of the time. So in other words, 3 out of 4 times that you drop a chip from up here, you're going to land somewhere between these 2. Now, again, these are all based on random falls, so they're just percentages. But what this tells you is, again, most of the time you land directly under the chip drop point, which means most of the time you're hitting the average. When I looked at the wall, believe it or not, I was expecting this to look a lot different, and it's not that much different. The wall, I read the Wikipedia page says it's 4 stories high. I actually went and opened a couple pictures of it and counted down. I think it's 15 rows. I think it just looks so big because they're dropping a huge beach ball shaped thing versus a little tiny white
white plastic ball like an OMSI or a Plinko chip. So anyway, same basic idea here. Same basic idea here. When you drop a chip up at the top, it's more likely to land near the middle by a percentage-wise than it is to land out at the tails. But again, one more thing. What does this have to do with times of eye contact with schizophrenic patients or the average volume of a gas tank in a car?
Here's the connection as I see it. Think about something from our Star Wars list from earlier, hip breadths. I mentioned that hip breadths in human beings are normally distributed. What does that mean? It means most people have hips that are about average wide, and some have larger hips, some have smaller, and a very few have extraordinarily large, and a very few have extraordinarily small. What does this have to do with Plinko chips falling or OMSI balls dropping? Well, think of the ball hitting a peg and then going left or right as some factor that influences someone's hip size. I can think of many factors off the top of my head. Genetics is one. Are you genetically predisposed to have a certain size hip? And that genetics is a wide range that could come from any number of input variables. Environmental situations. Your environment. Could your hips change as a result of your environment? Gender. Could that affect your hip size? Diet. Exercise. Injury. I mean, those are 6 things off the top of my head. Off the top of my head. And there are many more. And those 6 things probably have lots and lots of subgroups. So every one of those 6 things or subgroups is like the ball hitting a peg and then heading off one way or the other, creating larger or smaller hips. And it's not just hips. It's the vitamin pills. It's the size of the gas tanks. It's the eye times of schizophrenic patients. It's the heights of Wookiees. All of those things are from a process, from a manufacturing, so to speak. Whether it's a bolt or whether it's a hip, it's a process. It's a series of situations that are either endured, risen above, absorbed, whatever, and at the end result, you end up with a product that fits on this beautiful bell-shaped distribution. For the remainder of the videos for today, let's look at a couple situations of things that are normally distributed for the same reasons we just spoke about, because of many, many factors that go into the creation of these things, and how we can use some percentages that we already know to establish some information about the populations they come from.